morning all, my name is Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about wavelet packets. So wavelet packet is a one type of image compression. So image compression is a type of data compression application that encodes the original image with a few bits. The main aim of the image compression is to reduce the frequency of image and store or transfer data in an effective format, and also reduces the time required for images to be processed in the specific system. The wavelet packet method is a generalization of a wavelet decomposition that offers a richer signal analysis. So if you are taking any of the wavelet packet, these are all under image compression. Wavelet for image compression. So if you are taking any of the wavelet packets, that is only for image compression. So before going to the wavelet packets, how we are using? So wavelet packets are using in a image compression technique. So what is the image compression? So image compression is nothing but we are compressing the data, not an image. If you are compressing the data, automatically the image will be compressing. Okay. Suppose I am taking the 3x3 matrix or 4x4 matrix. Maybe I will change the intensity values, or maybe we will change the size of the matrix. Okay, the data will be compressed, not the image size. So that encodes the original image with a few bits. The aim of the image compression is to reduce the frequency of image and store the transfer data in an effective format. So when we are reducing the time required for image to be processed in the specific system, so any of the system, we are taking not only the image compression, we are taking as a time with required to the time of the specific system. The wavelet packet method is a generalization of a wavelet decomposition that offers a richer signal analysis. So every wavelet packet that are waveforms indexed by three naturally interpreted parameters: position, scale, and frequency. So what is the position, scale, and frequency? So why we need all those things? So wavelet packets are mainly for image compression, but what are the interpreting parameters? What are the parameters for the wavelet packets for the image compression? Means position of the image, and scale means size of the image, and what is the frequency of the image. Suppose I am taking the input image, frequency f1, output image, frequency is f2. So f1 to f2, are we changed or not? From the input to output, the frequency is changed or not? Yes, we have the changed. Why? Because same frequency we are not taking. Why? Because I am going for the image compression. So image compression means maybe the frequency of the image will be changed. When we are going for the compression, then frequency will be changed. Then only that is called image compression. So these are the parameters. That means position, scale, and frequencies. These are the parameters for the image compression of wavelet packets. So what is the wavelet packet? Wavelet packets is the generalized approach of wavelet decomposition, which introduce a spacious area of the possibility of signal analysis, that is permits the better accordance of analysis to the signal, and it transforms the signal to the frequency domain level. The wavelet frequency or the wavelet transform divides the low and high frequency subband. In the wavelet analyzing, the signal is divided into an approximation and a detailed coefficients. So when we are going for the wavelet packet, it is a generalized approach of wavelet decomposition, which introduces the spacious area of the possibility of the signal analysis that permits the better accordance of the analysis to the signal. So when we are going for the decomposition, so at the output side, generally decomposition will be there. Input side, composition will be there. So when we are going for the decomposition, at the output side, it will be changed. So wavelet packet will take care of about the input and outputs. Why? Because image compression, it take care of wavelet decomposition also. and it introduces a spacious area of the possibility of signal analysis that is permits the better accordance analysis to the signal, and it transforms the signal to the frequency domain level. The wavelet transform divides the low and high frequency subband. At the wavelet analyzing, the signal is divided into an approximation and a detailed coefficient. So when I am going for the approximation, also divided into the next level. So every image we are going for the approximation level. Approximation level. Approximation level is for the image compression. It is for image compression. So every wavelet transform, the approximation is also divided into the next level approximation and in detail, and it continues this technique until they reach a particular level. But in wavelet packet analysis, the process is also achieved on detail. So when we are going on the wavelet packet is a part of the wavelet transform. The low filter and high filter outputs repeated to offer a more flexible and a complex analysis, and it composes the process of n level, maybe a n+1 method, and the decomposition. So every wavelet packet we are taking as a wavelet packet. Sometimes we are considering as a WP. So we are going for the decomposition, and in the decomposition, generally we are taking as a possibility of the low pass filter and high pass filter. So definitely we are taking as a low pass filter and high pass filter. So every wavelet packet, that is a decomposition of the signal at the output side. Finally, which filter you are using, low pass or high pass. Every image compression, definitely we have to take the help of filters. So low pass filter, which stage you are taking, high pass filter, which stage you are taking, that is a more important. So the approximation is divided into the next level and in detail. So when I am going for the next level approximation or in detail, a continuous technique until they reach a particular level. But in the wavelet packet analysis, this process is also achieved on the details. So wavelet packet is the part of wavelet transform. The low pass filter and the high pass filter output repeated. So low pass and high pass we are taking, but which stage we are taking, that is the output repeated offer more flexible and complex analysis. In composition process, n level may given as a n+1 methods. Okay, n levels we are taking as a n+1 methods. For the n levels, n+1 methods we are taking for the signal decomposition. So the equation for the wavelet packet is a Wn of x equal to n equal to 0, 1, 2, 3. Here already we taken n levels, that is a n+1 methods. So here I am taking n levels, n equal to 0, 1, 2, 3. Input is a Wn of x. If I am taking W2n of x, what will happen means root 2 summation k equal to 0 to 2n minus 1 into h of k into Wn of 2 minus k. So what is happened means here I am applying the filter for the input image. For the input image. So W2n plus 1 of x equal to root 2 summation k equal to 0 to 2n minus 1 g of k into Wn of 2x minus x. Okay, in that equation, what we are accessing means it is the output with decomposition without filters. Okay, in the first method we are applying the filters. In the second method, in the decomposition means we are removing the filter. Why? Because already we are getting the output, so there is no need of filters. So h of n and g of n is identical to the wavelet. W0 of x equal to 1 into phi of x is the scaling function, and W1 of x equal to psi of x is the wavelet function. So I am taking here h of k and g of k. So if I am taking h of k, g of k, but n equal to 0 to 3. So h of n and g of n is the identical to the wavelet, and the scaling function is a Wn of x equal to psi of x. So psi of x is the wavelet function. So another equation for wavelet packets has the ability to further degrade the area of wavelets to follows. V0 equal to V1 plus W1 equal to U1 plus U0 of 1 plus U1 of 1 equal to U2 plus U2 1 plus U2 U3. So is equal to UN or UN minus 1. So here V0 is the signal space between the V1 and W1. Between the V1 and W1, that is a V0. So the approximation and detail of V0 respectively U0, U0, U1, so on U2 or U1 minus N, that is a V0. N is the decomposition series, the wavelet packet decomposition tree equal to N equal to for the figure. So when I am taking the N equal to 0, 1, 2, 3, so on, but here V0 equal to, it will be depending on V1 plus W1. So V1 and W1 are the approximation values are there, but V0 is the respectively the signal space. So in the wavelet packet, decomposition of a signal results in a considerable redundancy and an increase in the number of wavelet bases, in which the size of the library will grow rapidly when the number of scale levels is increased, and redundantly the results in a substantial increase of both computational and storage cost. A pruning algorithm is needed for selecting a subset of nodes for signal representation considered suitable for a given application and reducing the computational cost. So when we are going for the wavelet packet, it is a decomposition signal, means at the output stage we have to removing the filters, then the results are considerably redundancy of the increase of the number of the wavelet bases, and the size of the library will grow rapidly when the number of scale levels are increased. So when applying the redundancy, the scale of the factors are increasing. So the resultant results of the substantial increase of both computational and storage cost. But a pruning algorithm is needed for selecting a subset of nodes for signal representation considered suitable for a given application and reducing the computational cost. So these nodes should provide a sufficiently accurate approximation to a given signal. So then these nodes means n equal to 0, 1, 2, 3, so on we are applying here. So these nodes are providing sufficiently accurate approximation to a given signal. Given signal I'm taking as a V0 equal to V1 plus W1. So the Shannon entropy is applying here for measuring the signal economy. So the Shannon entropy for finding out the decomposition of a signal, it is the measuring of a signal economy from the input to output. So what is the equation for Shannon entropy is equal to cost Shannon equal to summation of minus of n into s of n square into log of s of n square. So it is the Shannon entropy or Shannon theory to finding out the decomposition of the signal at the output side, to finding out the signal economy. So every wavelet packet is an efficient algorithm to finding the minimal entropy solution is considerably contracted. So each node of the analysis tree beginning with root and proceeding level by the level of these leaves compute both the entropy of the node denoted by EP, means entropy for parent entropy. So EP means entropy. For parent entropy and entropy of its four offspring denoted as EA, EH, EV and so on ED for two-dimensional wavelets. Every image we are taking as a two-dimensional x-axis and y-axis. So these two-dimensional wavelet packets of the decomposition, the parent is a two-dimensional array of approximation or detailed coefficient of offspring of the filtered. Approximation is the horizontal, vertical and diagonal in details. So an efficient algorithm to finding out the minimal entropy solutions in easily contracted. Each node of the analysis is a tree beginning and root proceedings. So we are here seeing here every of this equation is a root theory of Shannon. So the root and proceeding level of the level of leaves. Compute both the entropy of the node denoted as a EP for parent entropy and entropy of its offspring. Four types are there, that is a EA, EH, EV and ED for the two-dimensional wavelet packets. It is a decomposition process. The parent is a two-dimensional array of approximation or detailed coefficients. The offspring or the filtered approximation for horizontal, vertical and diagonal. So if the merged entropy of spring is less than the entropy of the parent, that is EA plus EH plus EV plus ED. So these are the four levels are there. These four levels, and what is the condition? One less than EP. One less than of EP. Include the offspring. EP is already we know that is the entropy. That is the offspring in the analysis tree. If the combined entropy of the offspring is greater than or equal to that running the father offspring, keeping only the parent is the leaf of the optimal analysis tree. We can write the another form of clarity. Okay, when I'm going for the entropy, what is the parent? What is the parent thing of the optimal tree? So if I'm taking the parent tree, that means the merged entropy of the spring is less than the entropy of the parent. That is the EA plus EH plus EB plus ED. That is 1 less than EP, including the offspring of the analysis. It is combining of the total entropy, that is 1 less than of EP, and the offspring greater than or equal to the running the father entropy or parent entropy, that is the optimal analysis tree. Okay, and these are the no leaf need when C1. If no leaf means there is no nodes are there, that is a no leaf node. That is the cost value of the node. The value C2 is the sum of the cost value of children of that node. So if I'm taking C1 less than or equal to C2, this is a condition when it will be marked as a part of the best basis group and cancel any marks in the nodes or the subtree of the current node. Okay, so that is a C1 double less than. If I'm taking the C1 greater than C2, what is the condition? The cost value node is replacing with C2. Cost with replacing. Here C1 less than or equal to C2 means the base of the best group cancelled by any of the node in the subtree of the current node. Cancel the node. So C1 less than or equal to C2, C1 is greater than C2. These are the two conditions for this one. And it is a structure of two-level decomposition of wavelet packets. Structure of two-level decomposition of two packets. Two levels means high and low levels. Okay, two levels. First L equal to low and H equal to high. So two levels means suppose LL, two levels. LL, another two levels. Okay, so here I am taking the 4x4 matrix. So in the 4x4, first one is a LL1, LL2, LL1, HL2, HL1, LL2, HL1, LL2. So 1, 2, 1, 2, 1, 2 and 1, 2. Here also LL1, LH1. Okay, LH. Here LL, lower, 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 higher, high, low, high, high. Okay, low, 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 high, high, low, high, high. Okay, here L1, L2, LH, H1, H2, LH1, LH2, HH. Okay, here L1, L2, LL, LH, HL, HH, LL, LH, HL, HH. Okay. So L1, L2, L1, H1, H1, L1, H1, H2, L1, L2, L1, H2, L1, H2, H1, H2, L1, L2, L1, H2, H1, L2, H1, L2, L1, L2, L1, H2, H1, L2, H1, H2. So the structure of two-level decomposition of wavelet packets. So it is another example of samples of fingerprint and iris. So fingerprint means it is the fingerprint and these are the iris. Okay. So it is the input fingerprint and it is the output fingerprint. What is the difference means? Here the brightness is very high. The blackish is very high. So that is the reason how many lines are there we are not finding easily. Why? Because the blackish is very high. So that is the reason how many lines are there in the fingerprint we are not finding. It is typical to find. So it is the output. It is I am used wavelet packet, wavelet transform. So it is a wavelet transform output. So then we are easily identifying what are the fingerprint size. So we are easily finding out the size of the how many lines are there, how many sublines are there in the fingerprint. Here also it is a input image and it is a output image. So it is a output image with wavelet transform. So this one is a gray color is very high. Gray is high. These are the identifying the image. So unidentified image is converting to the identified image with the help of wavelet transform. Here also some blackish is there, some due to some noise or whatever maybe. So where this one is converting to the identifying fingerprint. That is the fingerprint with identical wavelet transform. Here another of wavelet transform. But what is the difference means? Here I am using fingerprint image. It is a iris image. So in the wavelet transform is also using in fingerprints and iris. Okay, how we are finding out how we are changing the fingerprints from one dimensional to another dimensional. So here wavelet packets for fingerprint image. It is a figure A and figure B. What are the levels are there means 0 to 50, 100, 150, 200, 250. Okay, here 50, 100, 150, 200, 250 like this. So when going the width and height, it is also width to height 20, 40, 60, 80, 100, 120. 20, 40, 60, 80, 100, 120. So what is the range? Here I am taking from 0 to 120 height. Here 0 to 120 width. But here what is happened? 0 to 250 height. 0 to 250 width. So the width of the and height of the images are changing. We have reduced the image width and height. So from 0 to 250 to 120 is possible, or 120 to 250 is also possible. Okay. With the help of wavelet packets, we are converting from one size of image into the another size. Okay, one in pixels of converting to the another pixels. Here image A is a 0 to 250 of height and width. Image B is a 0 to 120 height and width. So if I need 250, easily I will change it. If I want to converting from 250 to 120 width, easily we have to change it. How means with the help of wavelet transform, we are changing the width or height of the fingerprint image. Here also same thing, the wavelet packets for the iris image. Here in the A and here figure B, what is the range means 0 to 250 and 0 to 250. It is the height and it is the width. Here also 0 to 120 height and 0 to 120 width. So the height and width. So here also I am changing from 250 to 120. Here 120 to 250. Is it possible? Yes, it is possible with erase of image with help of wavelet packets or wavelet transform. So the wavelet packet is a generalized approach of wavelet decomposition which introduces a spacious area of the possibility of signal analysis that is permits the better accordance analysis to the signal. The transformation signal to the frequency domain level, the wavelet packet divides into the low and high frequency subband. Only two levels are there, low level and high levels are there. Okay, when I'm going for the two levels, that is a low level and high level of the wavelet packet. The wavelet analyzing the signal is dividing into the approximation and coefficient. Then approximation is also dividing into next level approximation and continue this technique until they reach a particular level. So when we are going to the wavelet packets of two levels, that is a low and high levels, when it is helpful, these levels are helpful means the wavelet packet is the analyzing dividing into approximation and coefficient. Approximation and coefficient. So this approximation is also divided into an approximation, a detail coefficient. This approximation is dividing into a next level approximation in detail and continue this technique until they reach a particular level. So when the wavelet packet analysis, this process is also achieved on the detail. The wavelet packet is a part of the wavelet transform. The low pass filter and the high pass filter output repeated offer a more flexible and complex analysis. So if I'm taking the low pass filter and high pass filter, what it may be, when I'm taking the low pass or high pass, these are analysis, this achieved on the detail. The wavelet packet is a part of the wavelet, the low pass filter and high pass filter repeatedly to offer a more flexible and a complex analysis. From input, suppose I'm taking low pass filter, so then I'm taking high pass filter, then it is going to the output state. So if I'm going to the input, if I need a high pass, then I will take low pass and I will take the output. So depends on your application of the image, you have to take low pass and high pass repeatedly for flexible and more complex. And the composition process is n level may be given as n+1 method. Already we know that n levels are converting to the n+1 methods. n+1 methods for signal decomposition of the figure. So it is one example of wavelet packet decomposition. To compute wavelet packet, we begin with two filters of 2n. Suppose x of n is the input. These are the first level, second level. This I am converting to the 2. This one again I am converting to the 2 levels, g of n, h of n, g of n, h of n. So level 1, level 2. So again here g of n, h of n, g of n, h of n, g of n, h of n, g of n, h of n. How many are there means 2 levels. Here also 2 levels. 2 levels. Here also 2 levels. So every wavelet packet decomposition is computing with wavelet packet. We begin with 2 filters of length 2n. So 2 levels means high pass filter and low pass filter. 2 levels of filters I am using for the length of 2n. It is a one better example for wavelet packet decomposition. These are the references of wavelet packets. So finally what we discussed today, it is the wavelet packet using for image compression. Using for image compression. This image compression that is nothing but a data compression application that encodes the original image with a few bits. The aim of the image compression is to reduce the frequency of image and store or transfer data in a effective format. And also we are reducing the time required for images to be processed in the specific system. The wavelet packet method is a generalization of a wavelet decomposition that offers richer signal analysis. So When we are taking the wavelet packet, atoms or waveforms are indexed by three naturally interpreted parameters: the position, scale, and the frequency. So when I'm taking the three parameters, position, scale, and frequencies, these are the depending on your wavelet decomposition from the input to the output. So it is a generalized approach of decomposition of the wavelet, and these are the possibilities of the signal to analyzing to permit the better accordance analysis of the signal. When the wavelet packet divides into the low and high levels of the subbands. So these are the subbands, low level subband and high level subband, that are the in detail of coefficients. Okay, so these are the approximation dividing into the two next levels of in detail, a continuity of the technique until they reach a particular level. Wavelet packet analysis is the process of achieving the detail. So when we are going for the wavelet transform, the low pass filter and high pass filter, okay, low pass filter and high pass filters are both using repeatedly for the flexibility of complex of process. Okay, when we are going for the n levels, n+1 methods we need. So what is the equation for wavelet packet? Wn of x equal to n equal to 0 to 3, w2 n of x equal to square root of k equal to 0 to 2n minus 1 into h of k, and w2n plus 1 equal to square root of k equal to 0 to 2n minus 1 g of k. So if I am going for the wavelet packet with the ability of the degradation function, and the area of the wavelet is follows: v0 equal to v1 plus w1. Here v0 is the signal space and v1 and w1 are the approximation levels of the signal function of the image. So the wavelet packet of a signal is result in a considerably redundancy and an increase in the number of wavelet bases, in which the size of the library will grow rapidly when the number of scale levels are increased. The redundancy results in substantial increase of both computational and storage cost. But the algorithm is needed to selecting a subset of nodes in the signal representation for a suitable given application of reducing the computational cost. So low pass filter and high pass filters are the two levels or two subbands of the image. So the nodes should be provided in a sufficient accurate approximation to a given level. The Shannon entropy function is measuring the signal entropy. So when we are finding out the signal entropy or signal strength or signal economy with the help of Shannon entropy. So Shannon entropy with the proportion of cost of Shannon equal to minus summation n into s of n square into log of s of n whole square. S equal to Shannon entropy and n equal to number of functions, n equal to 0, 1, 2, 3, so on. And these are the three nodes are there, that is the tree beginning, root and the proceeding levels. So these are the computational levels, and what are the four levels of the entropy are EA, EH, EV and ED are the four levels of the entropy with two-dimensional wavelet packets of the decomposition of the signal. So the merged entropy spring is less than the entropy parent, that is the EA plus EH plus EV plus ED, that is called the parent entropy. Parent entropy. So it is 1 less than EP means 1 less than or equal to the entropy that include the offspring of the analysis of the combined entropy, and no leaf means there is no cost of signal is there. The value of the node is a C2. The sum of the cost value of the children of that node is a C1 less than or equal to C2. When C1 greater than C2, that means the cost value of the node is replacing with C2. It is a 4x4 matrix of the two-level decomposition of the wavelet packet structure. Okay. In that least left side, I am taking as a LL, LH, HL, HH. So it is like this. Here LL, LL, LL like this. So complete row is like this. So here also LH, 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 LH. Here HL, 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 HL. Here HH, 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 HH. So LL, LH, HL, HH are the 4 levels of the 2 level of decomposition of the wavelet packet. It is a wavelet packet decomposition with the fingerprint and iris. It is the wavelet packet decomposition of the fingerprint image with the 1 level decomposition and a 2 level decomposition with the levels are changed from 0 to 120, here 0 to 250. So there are 2 levels are there, 0 to 250 and 0 to 120. These levels are changed. And here also the levels are changed from 0 to 120 to 0 to 250 or 0 to 250 to 0 to 120. These are the levels of the wavelet packets of iris image. And the wavelet packet transform is a part of wavelet transform with the low pass and high pass filters outputs repeatedly to offer a more flexible and complex analysis with n levels with n plus 1 methods. And it is the wavelet packet decomposition to compute wavelet packet to begin with 2 filters of the length. So 2 filter with 2 levels. 2 filter with 2 levels means LL, LH, HL, HH. That means we are taking G of n, H of n is a 1 level, G of n, H of n is a 1 level, 2 levels. Here J of n, H of n, 2 levels. This is a 2 level, 2 level. So 2 level with 4. Finally, we are occurring the 2 level, 2 level, 2 level like this. Okay, 2 level function with 2 filters. That is a G of n and H of n. It is a best example for wavelet packets with 2 level and a 2 filter packet with length of 2n. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.